Well, we're not going to consider machines here in section 6.6. So frames and machines are similar in that they both contain multi-force members and sometimes two-force members. Machines are special in that, well, I guess frames are used to support loads a lot of times, but machines are generally used to transmit loads from one portion to another or one place to another. Maybe there's some mechanical advantage associated with a machine. It may be designed to do some work. You might consider it like that. So here's a simple machine. It's a pair of pliers. And we're going to apply 100 newtons of force out here, and we're going to try to clamp that little pipe at B. And we want to find out how we can do that. So best thing to do is to try to understand, I guess, first what's going on is there are two moving pieces, and there's a pin there. Obviously, if you squeeze it here, it squeezes it there. We can analyze this by drawing a free body diagram. So let's do that. Let's draw a free body diagram, simple free body diagram of the bottom part. So I'll just do it like this. Doesn't have to be super accurate, just kind of shows what's going on. Okay, so this is the bottom part. There's a pin here, so let's go ahead and draw the pin. There's a force being applied there of 100 newtons. And here, the pin, or the pipe, or whatever it is we're talking about, is pushing back is pushing that way on that part of the handle. In other words, what we've got, let's draw a free body diagram of just that round part. We're trying to pinch it like this. So whatever that pinching force is, this B, is going to transfer equal opposite to the handle here, or to the jaw. All right, so let's see what we got. Let's draw the rest of our forces here. I have an AY and an AX. Let me draw it the other way. Come on, get that out of there. AX there. Okay. If we want to find out what B is with that 100 newtons, all we have to do is sum the moments about A. So that's a fairly straightforward thing. Sum of the moments about A is equal to 0. So I have B times its lever arm. Again, the lever arm, it doesn't matter about the angle, but it's just that distance. So it's 50 millimeters. So 50.050 millimeters. And then the other thing I have is minus 100 times its lever arm, which would be 250 millimeters equals 0. So I can get the clamping force is equal to 500 newtons. All right, so that goes pretty fast to find the clamping force. If I wanted to find the reaction forces at the pin, then we have to go back to some of the forces in the X and the Y. So let's do that. Sum of the forces in the X is equal to 0. So I have AX minus, well, here I better put some components here. There's going to be a B, two components. It's a 45-degree angle, so this is 45. So this is B cos 45, and this one is B sine 45. So let's go ahead and put that in there then. So that'd be minus B sine 45 is equal to 0. So AX is equal to 353.5, and that is newtons. That's a newton. And some of the forces in the Y. So I have positive 100 minus AY, positive B cos 45 is equal to 0. So I can say AY is equal to 453. And what often happens in these machine problems and in any kind of machinery problem, we care more about the magnitude of the force at the pin than we'd really care. Well, I'll say we sometimes will care about the magnitude more than we care about the directions. So, but if we wanted to find the magnitude, we would have to do the square root of the sum of the squares. So that would be AX squared plus AY squared. And that's going to be equal to 575 pounds. And so that's the actual shear force that's going to be on that pin. We'll talk about shear and what that really means here in Chapter 7, but that's where we'll be looking at that. Now, what is the mechanical advantage? Mechanical advantage is equal to out over in. And in this case, I have 500 out and 100 that I put in. I didn't put in 200, I only put in 100. And so the mechanical advantage here is equal to 5. All right, so that'll be something that you'll need to be able to calculate. All right, here's another very common machine. This is a Vise grip. You probably have one in your tool drawer at home or probably in your pocket if you're a good mechanical engineer. I'm just kidding about that. But at any rate, so the way this works is you push some force here. It's got a little compounding mechanism here. There are actually 4 moving parts. This one and this one on the top, then the 2-force member, and there. So again, look for a 2-force member. It's going to be in compression. So how do I go about solving it? Let's draw the forces on the portions of the free body diagram. I have chosen to look at these 3 and not this one. And maybe after you get some experience, you'll be able to see why I did that. But let's go ahead and put the forces in. So I have 150, and then I have, this is my pin C. So there's going to be a CY and CX. Now the pinching force or the clamping force at E, I'm just going to put here at EY, I guess. Now let's go, before I draw what happens at A, let's draw the 2-force member. The 2-force member is in compression, so I'm going to draw it like this, where this is going to be A and B, and it will have 2 components. There will be an AX and an AY, a BY and a BX. Okay, so I'll go ahead and put those AX, AY, BX, and BY. And these forces transfer equal opposite to that pin at A. So I'll go ahead and put those in there. So I'm going to say AY and AX. All right, let's go ahead and finish it with the bottom one. I have 150 going up here. Here's where the pin or the 2-force member contacts the bottom part. So I'll go ahead and put there BX and BY. And then there's a pin over here at D. So I'll go ahead and put DX and DY there. Okay, with all the forces there, let's see what makes sense about where we can start. All right, so looking at the top, I have an applied force. I know that this is a 2-force member, but I have a bunch of stuff going on here that I don't have values for. This 2-force member, I can get some relationships, but I have no numbers. Down here, I have something I can work with. I have 150 here. If I sum the moments about D, I should be able to find dy. So I'm going to start here at the bottom. And again, only experience, I believe, helps you determine where to get started. Most of these problems take a lot of practice in order to be able to get good. So if you don't feel like I'm giving you quite enough homework, then you should drag out some more problems out of the textbook, and there are plenty of problems for you to practice on if you feel like you're struggling with how to get started and on the concepts. But I'm going to sum the moments about D. Sum of the moments about D is equal to 0. So in this case, I have minus 150 times 130 millimeters. I guess I'm leaving it in millimeters for this problem, plus by times 30 millimeters is equal to 0. So I have by is equal to 650. All right, if by is equal to 650, I could recognize that this is a 2-force member, which it is. I know that AX is equal to BX and AY is equal to BY. which is equal to 650. And I can look at transferring that into this analysis. So now let's sum the moments about C. What I'm looking for is this EY. But if I sum the moments about C, I'm going to have the plus 150, which is this force over here, times this lever arm, which is 130. Oops, times 130. Minus AY times 100 plus EY times 60 equals 0. I think I've included them all here. If I sum the moments about C, 150 times this lever arm, going in that direction, that's positive. AY times this lever arm, negative. And then EY times this lever arm, positive. And that's all I put there. I've already solved for AY. I've given that, and I can solve that for EY. So EY, which is the question, is equal to 758 newtons. So with a fairly short analysis, you can make a pretty complicated problem. You can solve a pretty complicated problem sometimes. Sometimes they're more difficult, but this one, even though it looked pretty complicated, turned out to be fairly straightforward. What is the mechanical advantage? Mechanical advantage is equal to the out over the n, which would be equal to 758 over 150. So in this case, the mechanical advantage is 5. Turns out that's the same as the other one, but I'm not sure that was intentional. But anyway, there we go. The mechanical advantage is 5. Now here's something I just want to show you. I'm not going to go through this very carefully, but just a little bit of review, really, of even from Chapter 2 and Chapter 5, as we've been talking about that. We know about sines and cosines, but really they are just ratios, and that's what that means. The side opposite over a hypotenuse is a ratio. So you can see some examples here of ratios. We've also used the force vector ratio. In other words, f of x is to 5, as f of y is to 4, as f is to the hypotenuse, which I've got there. And the forces in two force members, again, are similar. If you have a two force member, you have an ax is to 5, as ay is to 4. And then when you do that, you can get a lot of, and those are obviously all related to the sines and cosines. So anyway, walk through that and convince yourself of all that. And so now I just want to look at this problem again using just a little bit different approach. And you can kind of look and see how this one was done. I just did a different solution here of using different members, but in this case I used the two force member, the jaw right here, and the bottom. I didn't use the top part at all. I just used the jaw there and the bottom part in there. Anyway, you can walk through and see how I did it and see if this makes some sense to you. Again, either way is appropriate.